Good afternoon, Pak Arif and friends. For today's opportunity, we're from Group 1. We would like to explain about tunnel field effect transistor. My name is Rivaldo Varianto with an NPM of 1706064795, and these are my friends, Arik, Dery, Rian, and Arik, Dery, and Rian. Next. So our presentation is divided into four main parts: definition, working principle, comparison, and also the summary of an IEEE paper that Arik have found. Yeah, so for the definition, we can see that TFET here, hafnium oxide, indium arsenide, and PIN. So basically it stands for tunneling field effect transistor by Mr. Baba. He was the one who developed it. And its structure, as you can see, is actually similar to a MOSFET, right? But what differs it is the switching mechanism. And it is an experimental type of transistor. And just like what I've said, PIN, it means that it is positively doped, and this is negatively doped. And this is the gate in the middle. Next will be we can see here, just like what I've explained, the p-type, positively doped and negatively doped, and the middle one is intrinsic. So TFET is considered as one of the most promising devices with high energy efficiency. And we also see here that they have high on or off current ratio with low supply voltage. And by that, it means that if it can be supplied with low voltage only, we can make the transistor actually smaller, which is very good. And high on-off current ratio is very beneficial for a transistor because it's like a switching. And last but not least, they actually switch by modulating quantum tunneling through a barrier in which it can it's a wave phenomena, whereas in traditional MOSFETs, it is by thermionic emission over a barrier. Yeah, this is the last slide for definition. We can see that they are not limited by Maxwell-Boltzmann tail of carriers. So they're not limited, and they also have, like, for example, the metal gate technology in the TFETs. It is used to improve the gate controllability over the channel region. We can see here, starting from the source, channel, and drain, and the elaboration on how the energy or band gap decrease and etc. will be developed throughout this presentation. Yeah, next.
So the next one is the working principle. Before, let me introduce myself. My name is Arik Mahira. So for the working principle of the TFET, it uses quantum tunneling. So what is quantum tunneling? Quantum tunneling is phenomenon in quantum mechanics that when the wave function, or in this case, electron wave, can propagate to potential barrier. Next.
Okay.
To understand a bit easier, here given is the energy band of when the TFET is off state and when the TFET is on state. So when it's in off state, which means that no voltage applied to the gate, the energy gap between the channel and the valence is large. So electron jump, cannot jump or cannot tunnel. But when we give voltage gate to the gate, electron can tunnel because the energy band of the channel is decreasing. Next.
Okay.
The next one is the tunneling probability. I just want to state here that if the energy gap decrease and the electric field increase, the tunneling probability also increase. And it can be seen here from the voltage gate versus the current graph. When we give higher voltage gate, the current also increases. Next. The next one is ambipolar behavior. Ambipolar behavior happen when we give negative voltage to the gate and it will make a leakage current. Thus, we don't want it to happen, this ambipolar behavior. Next.
Okay, before I'm going to explain this comparison, I will introduce myself. My name is Dery Ramadan. So this is the comparison between TFET and also MOSFET. So actually, the structure of the TFET is very similar to the MOSFET, but their switching mechanism is different. Different between TFET and MOSFET that the TFET use band-to-band tunneling, while the MOSFET use thermionic emission mechanism. TFET and also MOSFET is the source region is engineered, which in fact defines the carrier injection from the source to the channel. Like you can see, this is from the picture A and also B. They are different, where the source of the MOSFET is with the N junction as the source, while the TFET is the P source. So injection in TFET allow very high on of current ratio, while MOSFET only restrict the source drain exchange, which works well on the MOSFET. It means that the in TFET the on current is low when we compare to the MOSFET, but an off current is significantly reduced compared to the conventional MOSFET. And then next. So this is the graphic of the TFET and also MOSFET. So as you can see, so this is the graph of the TFET and MOSFET. The first of all, starting the MOSFET carrier are injected terminally over the barrier, while TFET carriers are injected from the source to the channel due to gap fill in the band to the band tunneling. And then the picture it can be seen that the drive current of TFET is very lower compared to the MOSFET, which is considered as the most conventional FET. And the SS or sub-threshold swings of TFET is very lower than MOSFET, which is at around 16 millivolt per decade. And then next.
Okay, for the improvement of TFET, we're reading from journal called an improved silicon tunnel field effect transistor with a buried strain silicon germanium source. It is written by Zhao, Hartman, and Mantle, a member of IEEE. So the journal proposed an improved silicon TFET by using buried strain silicon germanium source. Next slide, please. Okay, so they fabricate the TFETs with a strain silicon channel. First, the layer are grown on biaxially tensile strain SOI, and the tensile strain in silicon and the compressive strain in silicon germanium will reduce the band gap energy values, resulting into band gaps of 0.8 EV for silicon germanium and 1.05 EV for strain silicon. And the source and drain activation was carried out in one-step annealing at 650 degrees Celsius for 1 minute. And the B+ type of silicon germanium source was formed by selective etching of the top strain silicon layer. Next slide, please. So the band gap energy values, as explained before, the tensile strain in silicon and compressive strain in silicon germanium will reduce the band gap energy values. 0.8 for silicon germanium, 1.05 for strain silicon. And the figure below shows the Silvaco simulated band energy alignment of the compressive strain silicon germanium on tensile strain silicon. Next slide. Okay. So the transfer characteristic for the simulated band energy values of the B+ silicon germanium source to the strain silicon channel are illustrated in the inset. Under a positive gate voltage through band bending in the strain silicon, channel leads to BT-BT from the valence band of the P+ type silicon germanium source of the conduction band of the strain silicon. And the TFET performance was significantly improved by applying a backgate bias. The backgate bias will be explained later in our presentation. And so the average SS remains at 80 millivolt per deck over an ID range of 3 orders of magnitude. Next slide, please.
Okay, so this is the IDS VGS curves, or the voltage and current for the drain to source. So we can see that since the valence band offset or the delta EV is equivalent to roughly 0.3 EV, the typical ambipolar behavior, just like what Arik have explained. So we can actually, in this case, the P branch is suppressed. So of course, it is good if we can reduce the ambipolar. And then the next one is by using a backgate bias, which will be explained later on. With the help of backgate bias, it actually improved the TFET efficiency significantly. And last but not least, we can see that here, I hope you can see my cursor. So we can see that there is a dotted line here is that it is actually decreases linearly with the temperature for the MOSFET in contrast to the TFET. So basically it's different. So you can see the temperature and the SS is actually decreases linearly. And we can see here the parameters. Maybe this will be elaborated later on.
So the next one is the simulated band diagram when the structure only use one bake gate in here. So the structure use silicon germanium, a strand silicon, which is 25 nanometer thickness, and buried oxide, which is 145 nanometer thickness. And when we give 8 voltage gate and 30 voltage gate voltage, the tunneling length decreases. Next.
Yeah. Okay.
Okay, so this is the structure of the TFET and then the simulation. So as you can see, this is the picture of the TFET structure, and then which is consists of the double gate and then drain and the source. So to propose the TFET structure with indicate structural parameters, there are many tips how to indicate the structural parameters. First, the starter it is heterostructure with buried strain silicon and germanium on the source to enhance the tunneling current. And the second, they also use a double gate like in this picture structure to increase the tunneling area. And the last is the doping of the thin silicon layer is not necessary. And then next.
Here's the parameters used in the TFET structure that Derry has explained. Next.
Okay, so this is the simulation using Atlas Silvaco. The first one is the simulated electron tunneling rate in the purpose of the TFETs. It is in the logarithmic scale. It is the distance between the drain, source, gate, and the materials. And so the next graph is the TFET transfer characteristic that have been simulated. Next slide. Okay. So as explained before, there's the backgate effect. So the backgate effect, it causes the BT-BT. A BT-BT is the band-to-band tunneling. It's vertically from the silicon germanium source to the new strain silicon layer and thus enlarge the tunneling area. Similar to the device structure, and the backgate bias also increase the band bending of the strain silicon channel surface, resulting in higher band-to-band tunneling currents when a top gate is applied.
Okay, so we have reached the conclusion. There are several points concluded by the authors, and yeah. So for the first one, we can see that the N-channel TFETs with a straight silicon channel and a silicon germanium source have been demonstrated experimentally. So after they have demonstrated it, it can be seen that there are several points that can be concluded. Like for example, the system actually also has high on currents and sorry, this is a typo, and a slight subthreshold slope SS of 80 millivolt per decade at 300K, and just like what Rian have mentioned, it is for a 3 order of magnitude. And with an increased current on or off ratio, in which I've explained before that if it's a higher current on or off ratio, it will be better for the transistor because it's like a switching the concept. And it can be said that biased backgate. So biased backgate is very crucial to improve the efficiency of the TFET. And finally, the structure which have been proposed by them with a buried silicon germanium source at and top and bottom silicon channel, they have proposed it, and it can be concluded that the efficiency is greatly improved. That is it from our group. This is the reference for our paper. This is the references of our websites. Thank you very much and have a great day, everyone.